Hello. In our discussion of thermodynamic properties of the systems, we have been using several thermodynamic variables or coordinates like the pressure, the volume, temperature, entropy, internal energy, etc. And we have seen that the physical quantities or the functions in thermodynamics are usually classified into two groups. One may be the state functions or state variables, otherwise known as the point functions, and the other category is path functions or path variables, depending on whether the values of these functions changes with the path adopted or not. So you know that the functions like pressure, variable, temperature, entropy are all identified as state functions. They have got definite value at different states, thermodynamic states of the system, and the values of these functions are independent of the path followed by the system in going from the initial state to the final state. Also, we have familiarized ourselves with other quantities like work and heat, which were identified as path dependent quantities. Now, in the discussion that we have done so far, we have familiarized ourselves with the first law of thermodynamics, which is nothing but a restatement of the law of conservation of energy. The second law of thermodynamics, which decides or which defines what all processes are permitted and the direction of such processes, in what direction a certain process can occur. And during the discussion of the second law of thermodynamics, it was the time when we defined the quantity known as entropy, and we have seen that entropy has got significant role in defining the direction of a spontaneous process. Now, there are still several questions that are remaining unanswered. We are not able to completely describe the state of a thermodynamic system with the variables that we are familiar so far. And it was understood that for different situations or for different state of the system under different constraints, by constraint we mean certain limitations. If we define some new functions, if we are able to define some new functions, then it will be convenient for us to study the properties of the system in an easy manner. And it was due to this reason that a number of new functions which are functions of these thermodynamic state variables like pressure, volume, temperature and entropy were defined, which if you use along with certain equations which we are familiar, like the state equations, then it will give us a complete knowledge of the thermodynamic state of the system. It means that we are defining mathematically some set of new functions now, in addition to the already known state functions, which will help us to identify the property or study the property of a system, especially under equilibrium conditions. And such set of newly defined functions are named as thermodynamic potentials. So that is our topic today. We are going to learn in detail some new functions, not entirely new. Some of these functions already we have discussed, but we will give them a special status. We will give them more importance, and we will try to analyze our thermodynamic system in terms of these newly defined variables. So these newly defined variables will be named as thermodynamic potentials. See the word potentials that we are using here. See why we are naming these quantities as potentials. It's from the concept that we are borrowing from mechanics. In mechanics we define, for example, gravitational potential, and in relation to potential energy, potential is defined as a state function. Okay, so at every point in a field we define a corresponding potential, whether it is gravitational field or it is electrostatic field. Corresponding to every point in a force field we are defining what is known as a potential. Okay, and if an object is taken from one point in the gravitational field to another point in the gravitational field, there will be certain work done. Okay, and the work done depends not on the path followed, but only on the potentials at the initial state and the final state, and that is what we define in terms of the potential energy, right? So in mechanics, potentials are defined as state functions. That is one thing that you have to remember. But potentials are scalar quantities, moreover they are state functions in mechanics. So this concept of potential in mechanics has been taken to thermodynamics, or this is a concept that is analogous to the concept of potential in mechanics. It's a borrowed concept from mechanics. So why we call these functions as potentials? Because these functions that we are going to identify have properties of the potential functions in mechanics. That is why we are calling these newly defined functions as what is known as thermodynamic potentials. Okay, and why? What is the property of potential function? Potential functions are basically state functions. Potential functions are basically state functions, and these potentials are having dimensions of energy. They will have the dimensions or units of energy. Such functions are known as potential functions. Okay, and we are going to discuss the four main thermodynamic potential under this topic. We have identified several number of thermodynamic potentials, or several number of such functions which are broadly called as thermodynamic potentials, but we will restrict our discussion in this course to only four of them, and the four thermodynamic potentials are hereunder. The first one is of our interest, is nothing but the internal energy, or better we will call now as internal energy function. And this is the same function that we have been using so far, right from the beginning of our thermodynamic or thermal physics course, but now we give it a better status, and we will realize that this internal energy function has got a special status. We will understand how. Along with some other functions, it has got some supreme status. Okay, now another, so this is the first or one of the four important thermodynamic potentials we are going to see. The second thermodynamic potential is nothing but enthalpy. Enthalpy, the simple for enthalpy is H. It's also known as enthalpy function or heat content of the system. That is the other way in which it is known as. Enthalpy is yet another thermodynamic potential. Now another one is Helmholtz function. Helmholtz function. Helmholtz function is represented commonly by A, the letter capital letter A, or another equivalent symbol is F. So different authors and different books will be using different symbols. The common symbols are capital A or F. Helmholtz function, it's F, and F stands for some free energy. We'll see. Helmholtz function is also known as Helmholtz free energy. We'll discuss about this these functions in detail in the coming slides. Now, the fourth thermodynamic potential that we are going to familiarize ourselves is Gibbs function. Gibbs function, and it is also known as Gibbs free energy. The symbol is capital G. I think this enthalpy, Gibbs free energy, all these quantities you are already familiar actually. For example, see, whenever you learned your the chemical kinetics, okay, so the rate of chemical reaction and all, or spontaneity of chemical reactions, in maybe I don't know whether you are learning it right now in your complementary course, okay, but I'm sure that you have learned about how to predict whether or not a chemical reaction will be spontaneous or not by calculating what is known as the Gibbs free energy. In your plus 2 classes you have done it, or plus 1 classes you have done it. You calculated the change in the Gibbs free energy G, delta G, and depending on whether the delta G of the reaction is positive or negative, you concluded that the reaction will be spontaneous or non-spontaneous, right? Hope you remember that one. So that same Gibbs free energy is this Gibbs function, remember. At that time we were not using such names like thermodynamic potential and all. We were using certain functions because it was just an introductory course to thermal physics or chemical kinetics. But remember, these functions are already well defined and have been identified as one of the important variable or one of the important physical quantity which can give you a very important or a useful information regarding the equilibrium properties of a system under different situations. See, that is the significance of thermodynamic potential. So what I have highlighted in red here is the importance of thermodynamic potentials. So these thermodynamic potentials are nothing but certain functions of already defined thermodynamic coordinates like pressure, volume, temperature, entropy, etc., which if you use along with some other equations will be giving you a complete description of the equilibrium properties of the system. That is what I have to highlight. So these functions are useful in studying the equilibrium properties of a thermodynamic system under various situations. And what is meant by this situation, I will tell you. And these various situations, or I can say various constraints. Constraint means some conditions. Constraints means limitations or conditions. So what is meant by thermodynamic limitations? We put conditions that the pressure should remain constant, or temperature should be maintained as a constant, volume should be maintained as constant. These are all what is commonly known by the name constraints or limitations, and these are the different situations. Okay, so to summarize what I have done, what I have described so far, we are going to familiarize ourselves with some new set of physical quantities or new set of thermodynamical variables or functions which are mathematical functions of the already defined coordinates like pressure, volume, temperature and entropy. And what is their use? These quantities will be useful in studying the equilibrium properties of a thermodynamic system under various situations. And these functions are also known as thermodynamic functions, or also known as characteristic functions. Characteristic functions. We will understand why they are known as characteristic functions from the discussion that is going to follow. And I told you there are a number of such quantities defined in physics or thermodynamics. And our focus in this course will be on 4 of them. And one of them already we have been using right from the start of the course, which is nothing but the internal energy function. And the 3 of them At least two of them you have already heard in your lower classes. So these quantities are collectively, the group of these quantities or these quantities are collectively known by the name thermodynamic potentials. Okay, remember that this list is not comprehensive. This list is not complete. There are other quantities, okay, like grand potential and all, grand potential, phi and all, that we will be using usually, okay, in higher discussions. So phi, so these are also okay thermodynamic potentials. So depending on the situation, we'll be defining new and new thermodynamic potentials. I will tell you how you are defining this one, what is the technique, what is the motivation behind defining such new functions. I will tell you in the course of time, okay, maybe in the next session or something like that. Okay, so for us, the thermodynamic potential as far as our course is concerned are these four physical parameters: U, H, A and G. U, H, A and G. These four quantities are the thermodynamic potentials that we are going to discuss. And in the next video, I will be introducing each of these thermodynamic potentials, and we will be discussing its basic properties. Remember, the concept of thermodynamic potentials is one of the critical concepts in understanding the thermodynamics of real systems. And you will see that this concept will be used invariably in studying statistical mechanics in your postgraduate courses especially. And they are so related to equilibrium properties that with a mere knowledge of their values, you will be able to predict whether or not a system has achieved equilibrium. And you know, one of the way in which you can understand whether or not a system has achieved equilibrium is to check whether the entropy of that system has reached maximum, because we have seen that at equilibrium the entropy of the system will be achieving its maximum value, and it becomes a constant maximum value at equilibrium. So there are several other methods to understand equilibrium properties. So we'll see the discussion in the coming session.